Well, next we're going to talk about the intermediate value property for derivatives. And it's theorem 4.11. And before I write out the proof, before we even state it or prove it, let's draw a picture of what we're going to be talking about. If we have a differentiable function that maybe looks like something like that, well, let's pick 2 points. Let's say that's x1, and let's say this is x2. It's a differentiable function. Well, let's take the derivative at x1. The derivative at x1 would be the slope of this tangent line at x1. And the slope of the tangent line at x2, let's see, the line would look like this. So if I had to guess, I would say that the slope of that line, I'll call it m1 for the slope, is up 1 over 2, is maybe 1/2. And the slope of the tangent line at x2, that looks more like up 2 over 1. So I'll say that is m2, and it's 2 over 1, or just 2. What the intermediate value property for derivatives says, that for every number in between 1/2 and 2, say for example 1, there is a point somewhere between x1 and x2 that has a slope of 1. Probably right about it at that point. But every real number between 1/2 and 2, there will be a point somewhere in here that has a derivative of that, having that value, somewhere between 1/2 and 2. All of the numbers from 1/2 to 2 in this picture. So the statement of the theorem goes like this. If f is differentiable in the closed bound at AB, and lambda is an R, is a real number, an element of R, such that lambda is in between f prime of A and f prime of B, either in this order or in this order. So I could have just said that lambda is a number in between, strictly in between f prime of A and f prime of B. Then there exists a C in between A and B such that f prime is going to equal that value of lambda. Okay, well, let's start the proof. Let's start off by establishing a new function here. Let g of x be f of x minus lambda of x on AB. Notice that's a differentiable function. This is f of x, which is differentiable, and lambda x is just a straight line with slope lambda. If we said g of x equals lambda x, we're subtracting two differentiable functions, so we get another differentiable function. So let's notice something about the derivative. We can compute the derivative of g of x. G prime of x is f prime of x minus the derivative of this, which is just lambda. G prime of x is equal to f prime of x minus lambda, and that's on AB, on all of AB. Okay, so now let's cover both cases. Let's assume that first. So f prime of A less than lambda less than f prime of B implies, well, let's see. If I subtract lambda from both sides, from all three sections here, I would get f prime of A minus lambda, which is just g prime of A, less than 0, less than g prime of B. So that's what we get when we subtract lambda from all three sections. F prime of A minus lambda is this. Lambda minus lambda is 0. F prime of B minus lambda is just g prime of B. So we can see that g prime and, well, let me before I make any concluding statements, let's just notice that for the other case, f prime of a greater than lambda greater than f prime of b implies just switch the less thans into greater thans. Well, in either case, we get a positive number, a negative number, and a positive number. Negative number and a positive number. So in either case, g prime of a and g prime of b have opposite signs. Maybe I'll continue on here. And there exists a C in between A and B such that G of C is going to give us a 0. G prime of C is going to give us 0. Justification for that, you could say Bolzano's theorem or intermediate value theorem. I don't recall the exact number. All right, therefore, 0, which is g prime of c, which by definition is f prime of c minus lambda. So 0 is equal to f prime of c minus lambda. So that means that f prime of c is equal to lambda. And that's exactly what we tried to prove, or exactly what we proved.